our September Data Science webinar. It is sponsored by ASA Statistics Marketing Section. If you are not a member of Statistics in Marketing Section, please consider joining us as a member. We provide a lot of resource about statistics and data science. If you are interested in our previous talk, you can go to scientistcafe.com. There's a list of our previous talk and also the future talk. If you are in the live broadcasting, you can submit your question using the chat function on YouTube. Today we have Professor Ryan Dew from Wharton School of the University of Pennsylvania talks about his research on Bayesian nonparametric customer-based analysis. So now I will turn it to Ryan.
Great.
We should be able to see you now.
Great. Thanks, Hui, for having me here, and it's a real pleasure to be here. I was very fortunate to receive a dissertation award from the ASA Statistics and Marketing section, and so the work that I'm going to talk about today is based on that dissertation. Specifically, the title of my dissertation was Machine Learning Methods for Data-Driven Decisions. And today I'm going to talk about actually two, at least I hope to talk about two parts of that dissertation. So I'm going to do that through some slides. So specifically today, I'm going to be talking about, as I said, my dissertation. And specifically, I'm going to be talking about two parts of this dissertation. The first is broadly on the topic of customer analytics, and it's a paper titled Bayesian Nonparametric Customer-Based Analysis with Model-Based Visualizations. And then towards the end of the talk, I'm also hoping to have time to talk about the third essay of my dissertation, which is about data-driven design, and it's a paper called Letting Logos Speak: Deep Probabilistic Models for Logo Design. So let's jump right in. So this first paper, as I said, is about customer analytics and understanding and predicting how customers are going to spend in the future. Specifically, it's motivated by this idea of understanding and predicting purchasing, meaning answering questions like how much will a given customer purchase in the future? Or how do customers acquired through a given channel tend to purchase? Or how do things that we as the firm do relate to changes in customers' purchasing rates? Or even things like how valuable is a given product vis-a-vis that product's customer base? Specifically, we're going to be looking at questions like this in the context of a firm that has many products, so there's some need to automate the process of answering these kinds of questions. When we think about the dynamics of purchasing within a customer base, meaning the rates at which people are purchasing over time, there's a large body of literature that indicates that there's something that can be called the natural purchasing cycle. That is, that customers tend to arrive at the firm and then spend with the firm and then maybe churn or leave the firm at sort of characteristic rates that may be specific to that product or to that company. This is the idea that's captured by a lot of customer-based analysis and CRM models, models like hazard models, RFM models, or latent attrition models, which are sometimes called buy till you die models. The idea behind all of these is that this process, this natural purchasing cycle, can be characterized by individual level effects, things like recency, meaning how recently a customer has spent with us, or how long a customer has been with our firm, that customer's lifetime or tenure, or how many times has that customer spent with us in the past, that customer's frequency. These are the sort of sufficient statistics that have been shown time and time again to really robustly predict how active a customer is and how likely a customer is to come back and spend with us again in the future. But we all know, whether we're in marketing analytics or not, we know that there are other things that influence when somebody purchases. One natural candidate for something else is what I'm going to broadly refer to as calendar time events. That is, events, trends, and shocks that happen that are either controlled by the firm or just kind of happen in the world. So for instance, the firm may launch a new promotion or add new content to a website or a platform. There may be a holiday or a weekend or a platform outage, which changes the rates at which people are purchasing. Or a competitor of ours may do something that changes the rates at which our customers are spending. All of these things can have both short and long run effects on the rates at which customers are purchasing, so that they're pretty important for us to be able to capture and predict into the future if we want to understand how often our customers are going to spend. But the tricky part of this is that oftentimes things that fall into this blue box here may be a priori unknown. That is, if you think about a platform outage, we don't know that the platform is going to go out tomorrow at 10. I mean, in some cases, maybe we do, but oftentimes we don't. Or we don't know that a competitor is going to do something next week that's going to change the rates at which our customers are purchasing. Or even if, say, our firm is a big firm, there's multiple divisions managing marketing and analytics, we may not even know that there's a promotion happening within a particular product. Remember, we're thinking about firms that are managing many products simultaneously. And so it then becomes a real tricky task separating out these kinds of things from the natural purchasing cycle. But as I said, it's important to do so because we want to be able to forecast both of these sets of things accurately to get a very good understanding of how likely customers are to spend, so we can carry out kind of fundamental marketing tasks and answer those questions from the beginning of the talk. So what we're going to try to do in this work is we're going to try to decompose purchasing into these two buckets here. That is, our goal is an automatic decomposition that doesn't require any intervention from, say, like a human marketing manager. We're going to start with just individual level purchasing data, meaning something like an event log of when a given person has purchased in the past. And we're going to try to decompose that into the two sets of effects that I talked about before. So from this simple event log, we want to decompose that into the set of calendar time trends and shocks, that blue box from before, both what's happening in the long run, what's happening in the short run, and if there's any cyclicality there, things like, do people spend more on the weekends or not? And we're going to separate that out from these things that characterize the natural ebb and flow of purchasing, or that natural purchasing cycle, the effects of recency, lifetime, and purchase number, which, as I've said before, have been really robustly shown in the past to predict how active a customer is and how likely a customer is to spend again. So our goal is to get these sets of effects so that we can talk about what's happening both in calendar time and at the individual customer level in terms of repeat purchasing, without needing to specify that there were specific events going on in time, which these blue curves at the top may correspond to. And so what I'm going to spend the next, say, 20 minutes doing is building up to how we get these curves and then discussing what these curves actually mean. So the main contributions of our work are to, as I said, automatically separate out the short and long run impact of both known and unknown calendar time events from these reliable predictors of individual level purchasing. In doing that, what we're going to do is we're going to recast this traditional customer base analysis problem as a problem of estimating unknown latent functions. Rather than, say, the more traditional approach of looking at distributions, we're going to cast this as a problem of estimating unknown functions. And then we're going to estimate those unknown functions with Bayesian nonparametric Gaussian process priors. The end result is going to be managerially relevant insights via model-based, what we're calling model-based dashboards, what you saw on the previous slide. And what we're going to show is, beyond just getting this deeper understanding of what's going on at the customer level, we're also going to, by doing all this in such a flexible fashion, we're going to get a significant improvement in forecast accuracy over a bunch of different benchmarks. The data that we're going to use to show all of this comes from the world of free-to-play video games. Specifically, we have individual level purchase incidence data, just like I showed a few slides ago, where we're just tracking IDs and the times that someone spent. In this case, the things that are being purchased are in-game upgrades. So I'm playing this game and I want to get the best stuff. Sometimes I have to spend money to get that good stuff. We're going to be looking specifically at two games, one called, which we are going to refer to as Life Simulator. This is not the actual title of the game. And another which we're going to be calling City Builder. Again, not the actual title of the game. Specifically in both of these, in each of these, we're going to look at a cohort or cohorts of size 10,000 customers. So just a random sample of 10,000 customers who installed the game in a 1-month window of time, where the very first possible install date we're going to label as t=1, and then installs are going to happen for the next 30 days. And so this is the cohort which we're going to be tracking. The plots at the bottom of this slide show you the rates at which people are purchasing within each of these two games. So for Life Simulator and City Builder, we see at the start as people are coming in, installing the game, spending goes up. It stays at some rate for some period of time as we have this mix of installs happening and people repeat purchasing. And then it tends to fall off over time as people may stop playing the game, they may leave the game, they may leave the firm. This is what we refer to as churn. So people are churning, and this is why we see in both cases this downward slope towards the end of the period here.
So from time 1 to 30, it's a combination of purchase and installment, right?
That's right, yeah. So what we're plotting here is just the purchases. But okay, why it's going up during that period of time is that we're having these new customers coming in.
Cool.
And so, so what we see across these two is that the patterns are very, very different. This could be due to a number of things. This could be due to the fact that the purchasing rates, that natural purchasing cycle is just different across these two games. Maybe one has a higher churn rate, maybe one has a stronger recency effect. Or it could also be due to the fact that there may be something going on in calendar time. Think a holiday, think something that the firm is doing that's changing the relative rates of purchasing across these two things. And yet we as the analysts may not know about the existence, the even existence of these things going in. And so again, our task is going to be to figure out, to try to explain why these curves look different and to characterize these different purchase rates. The framework which we're going to use to do that is as follows. So we're going to be looking at people I at time t, where t is a day. And we're going to look, as I've already mentioned, at 3 key individual level predictors of purchase propensity. These are recency, denoted by R, meaning how long it's been since someone most recently purchased. Lifetime, denoted by L, meaning how long it's been since a given customer first purchased. And the purchase number, which we're going to call Q, which indicates how many times a customer has purchased in the past in total. This is sometimes also called frequency. And the actual framework which we're going to do this analysis is pretty simple. It's actually just a kind of a binary logistic regression, where we're modeling the probability that a given individual purchases at any given point in time t. That probability is going to be given by a sum of 3 components. The first component is the kind of primary point of interest, which is the propensity function, which describes how the rates of purchasing vary according to those individual level predictors above and calendar time t, which again, we may or may not know really anything about. The other components are just capturing heterogeneity, so how the customers are different from one another, both in terms of features that we can see, which are captured by Z, and maybe things that we don't know, which is given by that random effect delta I at the end. What we're going to assume in this work is that that propensity function F decomposes additively. So there's a time component, meaning a calendar time component. There's a recency component, a lifetime component, and a purchase number component. And so our task then, going sort of from this very general task of trying to detect changes in purchase propensity, now becomes a problem of estimating these 4 latent functions. And what we're going to do is we're going to estimate each one of these components non-parametrically with what's called a Gaussian process. And so what I'm going to do now is I'm going to describe in a little bit of detail what Gaussian processes are. If you're coming from a non-technical background, you can zone out for a few minutes while I kind of go through this interlude, and then we'll bring it back and we'll show how this all comes together in the practice of, for the purpose of understanding customer spending. So a Gaussian process is a structured Bayesian nonparametric approach to function estimation. That is, what we're going to be doing here is we're going to be placing a probability distribution over an entire function space. The the way we denote that is we say there's some function f here with a generic input tau, which would be either t or r, l, or q. We're just going to use this generic notation tau. Some function f is distributed as a Gaussian process, a GP, where this GP is governed by two components. One, a mean function, which captures the expected position of functions in this space. And the second is a kernel, which describes kind of the properties of functions in this space. I'm going to go over both of these components in a lot of detail in just a second. But what this means in practice, when I say that some function f comes from a GP with a given mean m and a kernel k, is that if we have, say, any given fixed inputs, meaning we want to look at this function at the inputs tau1 through tau n, then this is exactly equivalent to saying the outputs of the function evaluated at tau1 through tau n are distributed according to a multivariate normal distribution, where the mean is given by the mean function evaluated at each of these inputs, and the covariance matrix is determined by that kernel function evaluated pairwise at each of these inputs. So you can see what this GP is kind of like an infinite dimensional multivariate normal distribution, meaning the dimensions vary with how many inputs we actually have. And the properties of this are determined purely through that mean function m in that kernel k. And so their choice is going to be pretty important. It's also going to govern the kinds of results that we get at the end of this. For the mean functions, in this work, we're going to assume just two possible forms. We're going to assume that there's a constant, which is by and large the most prevalent assumption throughout the Gaussian process literature, and is also going to be sort of one of the dominant assumptions here. This is basically reflecting that we don't have any prior knowledge or any assumptions about what's going to happen to this function. We're also going to sometimes use a power mean function, which we're going to use to express the idea that we think this component of the function exhibits some kind of monotonic behavior. The functional form that we're going to use is given there on the slide, but it's more intuitive to look at the figure on the right. What we can see in the top panel of the figure on the right is, in some cases, depending on our final estimates, saying a function comes from a GP with this mean function, the end result may be very close to that mean function, as in the top row there. So we see on the left, it's basically constant. On the right, it mirrors this functional form given here. In other cases, though, we may find in the posterior, so this is the prior, when we add data to this, we may find, in fact, that the estimated GP is very far away from this mean function. And so the idea behind the mean function is that it gives us a prior kind of encoding of what we expect to happen. But by nesting this within a Gaussian process framework, we're allowing for non-parametric departures or deviations from this mean function. So we're not really restricting the forms that we may get out. Rather, we're allowing the model we're encoding our prior beliefs on top of this, which is going to help tremendously, especially when we get to forecasting later on. The way that the functions may deviate from this mean function assumption is captured through the kernel, this k that we had before. And here we're going to again assume two different forms. For most of the parts of our model, we're going to assume the top, which is called the squared exponential kernel, which lets us capture different traits of the functions, specifically traits that are the amplitude of the function, which is how much the function deviates from its mean, and the smoothness of the function, also called the length scale, which is that blue row squared parameter. And I've illustrated on the right the roles of these two parameters. You can see they kind of follow their names. The amplitude can either allow the function to deviate a lot or a little from the mean function, and the smoothness makes it either very smooth or very jagged. So this is the kernel that we're going to use predominantly throughout our work. Although we are sometimes going to also take advantage of this periodic kernel here. The periodic kernel captures periodicities of a given cycle length. So we may, for instance, expect a day of the month effect, and so we can include a 30-day cycle, or a day of the week effect, so we can include a 7-day cycle, things like that. And the reason that we need this is, especially for calendar time, we oftentimes expect cyclicality to operate on top of the maybe unknown effects that we also want to capture here. And so what we're going to do, especially for this calendar time part of the model, is we're going to actually layer these different kernels on top of each other. So specifically, we're going to take, say, the calendar time part of our model, or really any part of our model, and we're going to decompose it into what might be called long run effects, short run effects, and then any kind of cyclicality you want. In this case, we're going to use 7-day cyclicality. And the way that this is going to happen is by using, instead of just one kernel to capture the GP, we're going to use a series of kernels added together. So for instance, this expression at the top, long run, short run, and 7-day cyclic, can be captured by saying that my function f comes from a GP with a 3-part sum kernel, 2 squared exponential kernels which capture different levels of smoothness, one which may be jagged, like in the bottom row of the previous slide, and one which might be smooth, the smooth corresponding to long run, the jagged corresponding to short run. And then we're going to layer on top of that something that aims at getting at the cyclical part of this function, in this case, 7-day cyclicality, although you could put whatever cyclicality you want there. So this is going to get out, for instance, something that looks like this. So we've decomposed a given function into 3 parts. Again, a long run part, a short run part, and a 7-day part. And we've done this all just by assuming a specific kernel structure, which allows us to detect differences along these 3 dimensions. And so if that all went over your head, that's fine. Let's bring it back together here. Not here. We'll bring it back together here. When we're talking about customer-based analysis, we are going to be assuming a specific combination of mean functions and kernels, which is aimed at getting at specific traits of how customers purchase. So bringing things back together into the context of our model, recall our idea, our goal was to estimate these 4 functions: this time-varying function, this recency function, the lifetime function, and the purchase number function. Each of these corresponds to either this kind of perhaps unpredictable rate of spending with respect to calendar time, or to that kind of natural cycle of spending that we described at the beginning. For each of these components, we're going to assume it comes from a GP with a specific mean and a specific kernel. For calendar time, we're going to assume a constant mean function reflecting the fact that we don't have any, or we don't want to impose any assumptions about how this component of the model operates in the short or long run. And then we're going to build in a lot of flexibility in the kinds of effects that we're able to find here, actually exactly corresponding to the last slide, where we can allow it to find long run effects, short run effects, and periodic effects, all through the structure of that kernel. The other components of the model we're going to give a power mean function to, meaning we expect there to be some monotonicity here. This is very intuitive. For instance, if you imagine the recency component, what does this mean? It means if someone hasn't spent for 100 days or 200 days, we expect that that person is likely not going to spend again. That is, the more time that goes by without someone spending, the less likely we believe a priori that that person is really going to come back and spend again. And so we want to be able to capture these kind of perhaps monotonic effects with the model, but we also want to allow for departures from this kind of assumed functional form. And so we're nesting those power mean functions within, again, this GP framework with a squared exponential kernel, which is going to allow us to capture departures from that assumed mean. And so what does all this bias? What do we get out of this? Well, before I do that, I should say the way that we estimate this thing, we estimate everything in this fully data-driven fashion. So we're going to estimate both the function values, and we're going to estimate those hyperparameters, the amplitude and those smoothness or length scale parameters, so that the full thing is data-driven. We can detect the amount of smoothness that is indicated by the data. The way that we're actually going to do that, this is a non-conjugate model with significant posterior dependencies, and so we're going to rely on relatively recent, although now fairly mainstream technology called Hamiltonian Monte Carlo. Specifically, in most of our trials here, we've estimated this using the no U-turn sampler from Stan, although we can also estimate this with a variety of other HMC approaches, which may lead to computational advantages, which I'm not going to talk about in the talk today.
Sorry, Ryan,
yes.
Can you go back? Like, I think someone wondering plot. Which plot? I don't know. Which plot do you mean?
So the plot at the bottom here is the kind of what we're trying to get at with these calendar time component of the model. And I'm going to talk about that again in a second. Sorry if I was not very specific. When we're talking about the amplitude and the length scale parameters, what we're really getting at is this plot here. So we want to, the smoothness, meaning whether it's a long run component or a short run component, is really determined by that right-hand column of this, which corresponds to the value of that rho squared parameter there. And so by allowing for multiple rho squared parameters to operate along a single dimension, like time, we're able to isolate effects that look like this. And this is why we use this structure to model the calendar time component of the model on this slide, because we want to be able to be very flexible with the kinds of effects that we're capturing. We want to have both long run effects, which we think we can forecast into the future, and short run shocks to kind of absorb the noise or the temporary disruptions that are going on that we want to just kind of filter out so that we can really robustly predict all these other components of the model, which we know will do a good job at forecasting how likely customers are going to spend in the future. I hope that answers the question.
Yeah. Thank you.
So I'm not going to talk too much about estimation. If you're curious about what we've done here, I do have some code on my website, and you're also more than welcome to email me specific questions about that. What I want to get to is the results. What does this bias? What can we do with it? What can we do with all this? Somewhat anticlimactically, actually, I've already shown you the results, which is this, what we're calling the model-based dashboard. This was actually at the very start of the talk. And what this is that, again, it represents the nature of purchasing dynamics, both in terms of the shocks that are happening and the changes that are happening to the system in calendar time, given at the top by those blue components, and those that are happening with respect to the individuals. That is, how purchase propensity changes as a function of these three summary statistics on the bottom: recency, lifetime, and purchase number. And so this is the kind of decomposition that we were after, just going from that purchase log represented there on the left. What I'm going to do now is I'm going to kind of describe what each of these components of the model means. So starting at the bottom, what we can see in this customer base is we can see that if we look, for instance, at the magnitudes of these effects, we can see that by and large, the recency effect is massive. It's huge. What this is basically saying is it's saying that if it's been a long time since this customer has spent with our firm, meaning it's been 10, 20, 30 days, that customer is really starting to get more and more, or less and less likely to come back and spend with us again. So there's a really strong recency effect here. On the contrary, we don't see super strong lifetime effects. That is, we see that, yes, someone is seemingly more likely to start purchasing, to purchase at the very beginning of their lifetime. But after that, we don't see much variation there. And similarly with purchase number. If someone has purchased only once before, they're a little bit less likely to purchase now. But once they've purchased a few times, we don't see a big difference between somebody who's purchased 30 times and somebody who's purchased 20 times, or someone who's purchased 10 times. And so this is the kind of natural cycle of spending in this game. And we'll find actually in other games that this is really not, we see differences among these components. If we look at the top, though, this is a bit more interesting, because remember, our goal here is to kind of automate this process of understanding the customer base. And these curves reflect the kinds of shocks to the system, the things that we didn't really know about. The simplest one is this day of the week effect. This actually we kind of did know about. We expect in video games that people purchase more on the weekends than on the weekdays. And so this is the least interesting of the three. If you look at the other two, though, maybe the second least interesting is this spike that's happening here in the model. In fact, if you look over here in this plot here, you can see a spike here. And so you would expect that the model would find that there's something weird going on here. It's reassuring that it does find that. The function, the basic role of this short run function is to really isolate these shocks to the system so that they don't lead to the kind of equivalent of an omitted variable bias, meaning they don't mess up the other things that we're trying to estimate here. It's kind of like probabilistic trash collector or something like that. But in some cases, it actually has meaning. And in this case, in fact, it does. In this case, this spike corresponds to Christmas Eve, not Christmas Day, Christmas Eve. So people in this game tend to spend a lot more on Christmas Eve than they do on Christmas Day. I've heard a lot of explanations for why, or really more on Christmas Eve than on any other day of the year. I've heard a lot of explanations as to why Christmas Eve. Some of the more interesting ones are maybe it's people who don't have, you know, anything to do on Christmas Eve, and so they go out and play this game and simulate their own lives, which is a little bit the sadder interpretation of this effect. I like to think that this is probably parents buying their kids stuff to do to keep them busy on through the holidays. So that's a little bit more of an optimistic interpretation. But regardless, remember, we didn't have to know a priori that Christmas Eve was going to be this big deal of a day, because Christmas Eve comes out naturally. It's just right there. It appears in our dashboard. We didn't have to do anything. It just shows up. And so we can then say after the fact, okay, why is Christmas Eve there, and have conversations like the ones that I was just describing to you. In terms of the long run, we can see that there are two noticeable bumps in this curve as well. And again, we didn't have to specify a priori that we expected to find two bumps, but we do find them. And in fact, these two have interpretations, and in fact, very clear-cut interpretations. Specifically, during this first period of time here, roughly between days like 7 and 26, there was a game update, meaning they added some content temporarily into the game, which was meant to boost spending. Now, the cohort that we're looking at was relatively new at that period of time, so we don't really see a huge bump, but we do see that spending seems to have been higher and then lower during the period of this update. The next window corresponds exactly to the holiday time. You can see it aligns with Christmas Eve in the other panel. And so we see this big uptick during the holidays and then a sharp decrease after the holidays. This was also a period of time when there was a holiday update in effect. And so again, the cool part of this is we didn't need to say that there was this holiday uptick going to happen. We didn't need to put into the model that there was a game update. In fact, maybe we didn't even know there was going to be a game update because the game is managed by a totally separate team than the analytics is. But in this case, we still find that there's this effect of updating the game without specifying anything in advance. And so that's the interpretation of this. I already talked about this. Let's move on to the second game. I'm not going to belabor the explanation of this game, but what I will say is if you look, you do find effects in terms of calendar time, but you also find that the individual level effects, these red effects, are different. And these manifest in important ways. Specifically, they manifest in one of our key tasks, which is trying to predict how likely an individual customer is to come back and purchase with us again. That is, if we compare the nature of the effects in the one game versus the nature in the other game, we remember that relatively the recency effect was a big deal in the first game, and all the other effects were roughly flat after the first few days. Whereas in this game, we see both of these effects tend to kind of persist for a long period of time at relatively equal magnitudes. What this means is if we're trying to understand how likely an individual customer is to come back and spend with us again, we're going to see very different patterns across the games as a function of these sufficient statistics. Specifically, we're going to get patterns that look like this. So the way to interpret this is if I have some customer, say, who hasn't spent in 20 days and has been a customer of ours for 40 days, then that customer's respend probability is going to fall at this big blue X on that plot. And so what we can see comparing across the games is for the life simulator, if we care about whether somebody's going to come back and spend with us again, all we really need to look at is the X-axis. How long has it been since that person spent? On the other hand, if we want to understand someone in the city builder game, we need to have a grasp of all of these functions. That is, all of these are at work, which again may reflect differences in the kinds of players or the kind of game that's here. And so the last part that I want to talk about before moving on to the third section of my dissertation is how well does this do at actually predicting how people are going to spend in the future? So the forecasts here are going to be built partially by doing a really good job at capturing those individual level effects, and partially by predicting what's going to go on in terms of calendar time in the future, both in terms of cyclical components and that long run component of the model. And so what you can see, and what I'm going to show visually, is that our framework across both of the games does a really great job at forecasting out of sample. Again, this is driven mostly by those individual level components of the model being estimated really precisely without all that calendar time noise being there. And then layering on top of that, what is actually predictable about calendar time. So this table on the right is giving the fit statistics in terms of the in-sample fit, the out-of-sample fit. We see in-sample, the fit is just like this totally bizarre, incredible fit. This is not because, in fact, we can say generalize all of these little bumps. But remember, we had that short run component of the model, which I kind of described as the garbage collector, which I don't really mean. But basically, that component of the model is allowing us to detect all of those little blips. And so it's almost intentionally overfitting in sample. But out of sample, that part of the model basically goes away. We don't imagine that we can forecast that part. And so the GP actually reverts basically to zero, that component of the model. And so out of sample, we're left with just the smooth components of the model. The things like the recency effect, the lifetime effect, the purchase number effect, the long run calendar effect, and the cyclicality. These are the things that are driving the out of sample forecast. And we see that indeed out of sample, we're not picking up every little blip, but we're still doing a pretty good job at detecting the cyclical peaks and valleys and detecting the trend that's going on. And importantly, we're doing it better than basically any of the models that are out there in the literature so far. So we tested it against a bunch of candidates from the marketing literature, even some that we kind of just came up with on our own. And we see across all of these, we get a better fit with our framework. And the key idea here is that by separating out that unpredictable stuff, that short run stuff, from predictable trends and smooth individual level effects, we're able to get better predictions. So I think I have about 15 minutes, a little bit less than 15 minutes left. And so I want to wrap up my discussion of this paper. This paper is published in Marketing Science. So if you want to refresh any of the details, it's available. The basic summary of this paper is we've introduced this Gaussian process propensity model, which can automate the customer analytics process in these dynamic environments. Gaussian processes allow us to flexibly capture structure in latent purchase propensities, and this yields nuanced insights via, I think, easily interpretable model-based dashboards. We saw that we can get a kind of non-parametric effect estimate for both known and unknown marketing relevant events. And we're also able to do a good job at capturing individual level repurchase probabilities. What we find in terms of the forecasting is, as I said, by isolating predictable factors from unpredictable calendar time shocks, we get this very substantial improvement in predictive performance. And so that's what I have for that. What I want to talk about too, though, is this third essay of my dissertation. And the reason I want to talk about it is because it's something that I've been doing recently. It's something that I think is pretty exciting. And it was also, part of what I've used this very generous funding from the ASA for is continuing work on this part of my dissertation. So thanks again to the ASA for their support. So this project, as I have written here, is called Letting Logos Speak: Deep Probabilistic Models for Logo Design. In this, we're going to be looking at logos, and specifically, we're going to be looking at what logos convey about a firm. So this is, as you can see, a very different project from the first one that I talked about. I also don't have a whole lot of time to discuss the details of it, so I'm going to talk about it at a little bit of a high level, but hopefully I'll give you a sense of what we're doing so you can appreciate it or leave feedback if you're interested. So logos can first convey kind of what a firm does. If you compare, for instance, logos that come out of a fast food industry versus logos that come out of the tech industry, you can see that they have very different traits, not just in terms of their color schemes, not just the red and yellow versus the blue and black, but even in terms of their, say, level of detail, how bold they are, how many different colors they're using, whether or not there's bounding boxes around the different things. Whether or not there's like a one-to-one aspect ratio, meaning there's circles or squares versus their rectangles. There's very clear patterns that exist within industries and differences that exist across industries. It's not just even what the firm does that a logo conveys. They actually, in some sense, can also convey what the brand is, meaning, say we thought of brand identity. If we imagine that a brand is like a person, what personality would that person have? We can see, for instance, there's differences between the logos that people rate as the most daring companies versus the logos that people rate as the most tough companies. On the left, we see that daring companies tend to have just a single color. They tend to have sans serifon, although not all of them. They tend to have these simple marks, versus when we look at the tough companies on the right, again, they tend to be bold. They tend to have these really bold fonts. They tend to have some maybe italics in them. They tend to have red colors, yellow colors. And so there's a template for what kind of makes a firm daring versus what makes a firm tough, for instance. By harnessing these kinds of patterns, logo design can, in some sense, help consumers find what they're looking for. So this is one implication of good design, why we care about understanding these design patterns. If you imagine finding a good on a shelf in a store, say there's some product that's on this shelf here that I put in the gray box, and say you're going in and you're looking for the luxury brand. Finding that luxury brand on this shelf is a lot more difficult, just, I mean, in terms of time it would take or whatever, than if you were going to look for it, say, on this shelf, where we've designed the fonts according to our later findings, in which according to what makes something seem luxurious versus cheap versus strong. And so you can see there's maybe other things going on here too, but you can see that having a logo that's designed to elicit the kind of associations that you want as a firm can be really important in terms of consumers finding your product and understanding your product the way that you want it to be understood, or understanding your brand the way that you want it to be understood. And so our fundamental research question is, how do the visual elements of logos convey the brand identities of firms? That is, if we look at all of these different logos here, we can see that they're fast food logos. And so we want to know, what is it that makes something like a fast food logo? And then on the other hand, when we see some kind of interesting firm like Shake Shack coming into this market, what is Shake Shack doing by deviating so dramatically in terms of their logo? That is, by going from this classical red and yellow model to this thin, narrow black and green model of a logo. Why might they be doing that? What elements are they drawing on when designing their logo? And how is this working to attract the kind of customers or develop the kind of brand associations that they want to develop? And so this is kind of the kinds of questions we're going at here. Since I don't have a ton of time, I'm going to go kind of quickly through doing this. Our main contributions in this project are, we draw on prior research about design and theories about design to craft a logo feature extraction algorithm. This basically decomposes a logo into its constituent features, which we then use to understand design from a data-driven perspective. Specifically, this lets us do things objectively and at scale without relying on human coders. This also lets us do things holistically, weighing trade-offs among different design elements simultaneously. So we're able to consider both the font and the color and the shape and all these different things simultaneously in understanding what makes a logo work. We're also developing methodology for leveraging unstructured multi-view data, including images and text. And the end goal of this is to help firms make data-driven decisions, data-driven design decisions about their logos, but maybe also in other domains too. The data that we're going to use to do this was something that we compiled ourselves, which basically, it's data from 715 large high brand value American firms, where we're taking their most representative logos and we're taking a bunch of text describing these brands. And we're also taking brand personality survey data from Amazon Mechanical Turk. That is, we went out to Amazon Mechanical Turk and we asked a bunch of consumers to rate these 715 firms as if they were humans. So would you imagine this is a friendly firm or an honest firm, and all these things? And so these are the main sources of data that we're going to use to understand the underpinnings of design. In doing so, we're faced with two key challenges. The first is working with logos as data, meaning, as I said, how can we actually take some logo, like here the Hershey's company, and decompose that logo into constituent features which we can then understand. So that's the first thing I'm going to talk about today, this logo feature extraction algorithm. And the second thing is, how can we quantify design and brand meaning once we have this understanding? And so what I'm going to present very briefly today is some model-free evidence sort of getting at these correlations that exist. And I'm also going to present this model of logo design, which merges all this data that we talked about before, this text and these design elements so that we can then say, for instance, given some text about a firm, come up with the best, or not necessarily the best, but a typical logo that would convey the essence of that textual description. Or vice versa, we can let the logo speak for itself. That is, we can understand for a given logo what associations that logo is likely to bring to mind, and then get a better understanding of how logos convey meaning. So the first part of this is what I'm calling a logo feature extraction algorithm. And what we've done here is we've algorithmically decomposed logos into both design meaningful and consumer relevant features. That is, we want to not just work with things that are relevant from a computer or to a computer in terms of identifying a logo, saying like you would be if you wanted to detect whether there's a cat in the picture or not. Rather, we want to use features that a designer could take and make into a logo. And then we also want to capture features that have been shown in the past literature to be relevant for how consumers perceive brands. That is, we want to build on the sort of research that's come before, not just come up with our own totally new thing. And so the process is outlined here. I think this outline is not the kind of most intuitive. What's more intuitive is to see kind of what we do. The basic steps, though, are that we take some summary features of the logo. These are sometimes easy to get things. We then segment the logo into distinct regions, which we then classify in terms of whether they are a font, whether they are some kind of design element. And then we group all of these things that we've learned into a sort of dictionary, which lets us talk about what's in a logo. But it's easier to see than it is to describe. And so some of the things here, I'm using Amazon's logo as an example. Some of the things that we extract are, like I said, kind of easy things, like how much white space is there in a given logo, or how many corners are there in a given logo, or what is the kind of orientation of the logo, these so-called edge gradients, which will tell us if the logo is typically oriented to the right, to the left, upward diagonal, downward diagonal, and so on. Or what is the general shape of that logo as captured by what's called the convex hull, shown here as kind of this oblong rectangle slash oval. But we also get into some more detailed, maybe more interesting features, things like what are the different things that are going on in this logo? That is, there's a bunch of characters, and there's also something which we're going to call the marks. In the Amazon case, this is the little smiley face arrow thing on the bottom. So the marks and the characters we're going to treat separately. Characters are super important because brands and firms and designers spend a lot of time thinking about the fonts that best capture their brand. And so we spent also a lot of time too thinking about how we can understand fonts. Actually, we have our character identification system, which I'm not going to go into here, but lets us talk very richly about the fonts that are going into a given logo. When I talk about kind of a dictionary creation or feature creation, what I'm talking about is really taking all of these things that we've distilled from a logo and creating, again, something that would be meaningful to tell a designer. So it's hard to tell a designer, oh, you need to use this particular very specific color value. Rather, you could say the best color to convey what you want is bright red or bright blue or orange or gray. So we do things like create a color profile which captures representative colors and a bunch of different things along these lines to kind of describe logos, again, in design meaningful terms. The shape of the logo, the kind of mark that's in the logo, all these sorts of things go into our feature creation thing. For the next very few minutes that are left, I want to just show you some of the results that we get from this, because I think this is the kind of the very cool part. So the first thing I'm going to show you is just some basic descriptions. So for instance, how did I design this shelf here at the beginning? Well, what we can see if we kind of look at the data is we can see that, for instance, the dominant color of the logo varies, changes how people perceive a bunch of these brand personality dimensions. So if we look on the right, we have many of these dimensions that I was talking about before, like whether the brand is described as down to earth or honest. And we can see from the plot is showing, given I have a different color, say black, as my dominant color, how do the perceptions vary for if I have that as my dominant color versus I don't have that? So if we look, for instance, at this purple dot up here at the top in the black, what this is saying is that firms that have black as their dominant color tend to be perceived as much more upper class than firms that don't have black. And so you can see that, for instance, this is all these daring, spirited, imaginative variables are all very high for black. So is upper class. And so are things like outdoorsy and tough, which seems a little bit like a contradiction. We can find these same patterns across many of these different colors. And we can find these kinds of things too across many of the other features, things like fonts, things like the lightness, the number of corners, and all these different kinds of features here. I don't want to belabor this because I think we're basically out of time here. Is that right, Hui?
Yeah. Someone is asking, is that an unsupervised or supervised process? It seems like cluster segmentation is unsupervised. And in the end, you match it back to the outcome of the survey. That's kind of supervised, right?
So there's many different components at work here. So for the feature creation, a lot of it is basically doing unsupervised clustering. So that comes in at a whole bunch of different points, like when we try to determine how many colors there are going to be in the logo. What is a given, like say, what are the typical shapes that logos take, this hull variable, things like that. That's all unsupervised stuff. The results that I'm showing to you right now are, I would say they're not really anything. They're just kind of, they're mean differences, almost like a t-test of saying, given we have this feature, do we see that the people perceive things differently? And so you might call this supervised, but it's really kind of model free at this point. The later stuff that I'm probably not going to have time to talk about, but the later stuff that we're going to be doing is a kind of combination of supervised kind of predictive methods. So given we have a certain logo or given we have a certain personality, can we actually predict what would end up being in that logo from a personality, or can we predict how people would perceive that brand from its logo features? And then finally, we're going to create a kind of unsupervised multiview learning algorithm, which basically says, which basically learns a joint distribution across the different domains. So we could say, given one domain, what do we likely find in the other domain? I may leave that off because I know I'm kind of out of time here. So there's a bunch of different things that we've done here. Like I said, predicting different things. We also have a bunch of web apps available for generating logos that are consistent with brand personality. These are not quite ready for public distribution yet, but they will be eventually in the paper once we've got that, and that'll also go up on my website. And then the final component of this is this model of logo design, which kind of tries to capture all of these features jointly. We're using, as I said, this multi-view representation learning algorithm, which I'm certainly not going to have time to go into right now. And so I will just kind of show you maybe the most fun result from this, which is that we can use this kind of results from this framework to generate random brand identities. I think this is kind of fun thing to experiment with. That is, we can basically generate entirely new brands. So this is just one example. We've generated here some kind of, we've generated the words that describe the brand and also the features of the logo. And I think that hopefully viewers will find that this is a fairly coherent identity. So the scientific power, discovery, research, technology, breakthrough, et cetera, combines with a logo that has kind of condensed bold font with blue and yellow colors, that has a mark, that has low white space with high vertical symmetry. These things are a little bit hard to see in just the bullet points here. Hopefully down the road, we're going to build something that would actually take these features and make them into a logo. But I know that I'm out of time, so I am going to just kind of stop right there and thank again the ASA for giving me the opportunity, and thank the viewers for watching. If you have any questions, I'd be happy to receive them now or via email later. And both the first paper, the second paper, which I didn't have time to talk about, and the third essay of my dissertation, the first two are available online. The third one about logos should be available very soon on my website. So you can Google my name if you're curious about those. Thanks again, Hui and the ASA for your time.
Thank you very much. Do you have any question from the audience? One more question is about the feature. How do you extract the feature from text and image? I know from the just view the picture and you can see the color, but how you get that data using computer?
Yeah, so in terms of the, so is the question saying like, from where did we get that
data, the feature data?
So for the logos, for instance, we took just the most representative logo of the firm. So this is a little bit of a tricky thing. But we basically just sort of, for any firm, we'd look on their website, we'd look in their marketing materials, and we'd find the logo that seemed to be the most commonly occurring one. And this was the logo that we chose. This was very painstaking manual labor. For the text, we just took all the text from those firms' websites. So we took as much text as we could find from them, things that are hopefully describing the brand identity and also what the firm does. In terms of how we use this data, then there's that whole algorithm, which I gave a little brief overview of, but there's many components to this. The basic idea is that within the computer, images are represented as pixels. And so once you start, you start from this pixel representation, which can then lead to a bunch of different algorithms, some of which are canned algorithms that are just available through any kind of image processing library, which is what we use for some of the features. Other things we developed ourselves, typically using combinations of unsupervised cluster analysis and things like that, to kind of get at a very specific aspect of things. So for instance, the font part of things, we actually created a dictionary of representative fonts, which we then try to match every given letter to, in terms of figuring out what's a letter. That we do through a segmentation analysis, which is the initial step is based on clustering the different colors. And then we find regions that are separated by white space. So there's a whole lot of stuff that goes on in terms of how we actually get those features. If I had had a whole nother hour, I certainly would have spent some time talking about that.
Cool.
But I hope that gives a gist of things for the interested person.
Thank you. Is there any other questions? I don't see questions coming in. Thank you, Ryan.
Okay, great. Thanks again, Hui. Thanks again to the ASA for funding this research, and it's been a pleasure talking to you all.
Yep. Thank you.
Okay, bye-bye.